pH, pOH, and Kw. So pH is defined as the negative log of the H plus concentration. pOH is the negative log of the OH minus concentration. So lowercase p times anything means the negative log of that thing. And Kw is equal to the hydroxide ion concentration times the hydrogen ion concentration. And this comes from the fact that water can self-dissociate and creates an equilibrium. So it dissociates into OH minus ions and H plus ions. So remember that whenever we have an equilibrium concentration expression, we have aqueous ions. Anything that's liquid or a solid does not get included. So Kw is really just an equilibrium concentration expression that is working just with specifically water. So it can dissociate without any help, it auto-dissociates. So when water dissociates into H plus and OH minus ions, it will create an equal concentration of H plus and OH minus ions, a 1-to-1 ratio. But what I have here is a system at equilibrium, which means that it can respond like Le Chatelier's principle. So here's an example. If I add acid, really I'm adding H plus ions. So I see a hump in the H plus ion concentration. OH minus ion concentration stays the same. But in order to keep the Kw equal, what's going to happen is that I'm going to have to decrease my hydrogen ion by shifting left. And in doing so, it will take hydroxide ions with it. So my hydroxide ion concentration will go down. So in the end, I will see that both of these will be lower than what they were here in order to keep the hydrogen ion concentration, the Kw, to be constant. So water by itself, when it dissociates, is going to create equal concentrations of hydrogen ions and hydroxide ions. So there'll be X. So the Kw at 25 degrees Celsius is equal to 10 to the negative 14th. So X, which is the hydrogen ion concentration and the hydroxide ion concentration, will be equal to 10 to the negative 7th. The pH, which is the negative log of this, is equal to 7. That's where that magic number comes from. Here's an example. If I add 0.02 molar hydrochloric acid to water, what's going to happen is that the hydrogen ion concentration will increase, but in order to keep the Kw the same, my hydroxide ion concentration will have to decrease. This is my Le Chatelier's principle graph that we just showed right here. I'm adding my hydrogen ion concentration, and so in order to compensate to keep my Kw the same because my temperature doesn't change, my hydroxide ion concentration will have to drop. So HCl is a strong acid, which means that when I add 0.02 moles per liter of HCl, that's how many hydrogen ions I will be adding. So 10 to the negative 14th is equal to 0.02 times X, which is my hydroxide ion concentration. When I solve for my hydroxide ion concentration, that becomes 5 times 10 to the negative 13th. So it went from 10 to the negative 7th to 10 to the negative 13th because my hydrogen ion concentration went from 10 to the negative 7th to 0.02. Now you may be saying, well, according to my Le Chatelier's principle graph, I may be adding 0.02 moles per liter, but I'm going to see a decrease. But remember 5% rule, right? 5% rule basically says if at this point I'm at 0.02, that's many, many times greater than 10 to the negative 14th, which is my Kw. And as a result, this change right here is going to be so negligible, I can pretty much treat it as just 0.02. So again, it's supposed to be 0.02, but that 0.02 minus X ends up being 0.02 minus 0.00000000000000005. There's really no way that I can actually measure that. So we just keep it at 0.02. So my X is going to be equal to 5 times 10 to the negative 13th moles per liter of hydroxide ions. So I'm really increasing my hydrogen ion concentration. My pH, which is the negative log of that, would be 1.69. So knowing this, I can look at the relationship between pH and pOH. I could take the negative log of 5 times 10 to the negative 13th and find that my pOH is 12.3, or I can understand that if I take the negative logs of all of these things, basically I'm taking the exponents, that 14 is equal to my pH plus my pOH. So if I wanted to find my pOH, it would be my pH subtracted from 14, which will be 12.3. So if I have a pH of 4.5, I could also ask what's the concentration of the H plus ions. So the concentration is going to be 10 to the negative pH, so it will be 10 to the negative 4.5. Here's a side note, don't ever leave your hydrogen ion concentrations as 10 to an exponent that has a decimal in it. So you have calculators, plug that in, put 10 to the negative 4.5, and you'll end up with 3.16 times 10 to the negative fifth molar. So in a solution that has a pH of 4.5, my hydrogen ion concentration is going to be 3.16 times 10 to the negative fifth moles per liter of hydrogen ions.